I'm going to be honest, I'm going to feel this video is already done in the recordings that have been posted that summarized each of these individual topics, but I'm going to try and make them slightly more new and interesting, so if somebody watches them and finds something interesting, please let me know. So, here's our substitution and elimination, our basic components. So what we're concerned about are what are the individual aspects behind these that would allow us to kind of shift between one mechanism versus another. So substrate effects. This is at least new. We want to be able to go through and look at a substrate and be able to decide which mechanism it should favor, okay, or which process it should go for. So the first kind of principle that we're going to outline here is that we get our unimolecular or our one-type mechanisms, which we should remember as carbocations. And then we also have our two-type mechanisms, which we should be remembering as backside attack. Okay, which I'm actually going to write and then erase, because I think a better way to, or a more useful way to remember that might be sterics, okay, or steric hindrance. So we've got a bunch of substrates up here. If we go through and classify each of these, so what we're concerned about is where the leaving group is connected. Bromine's going to be our best leaving group. We'll discuss why bromine's a good leaving group in a little bit. Okay, so we look at that carbon, and we want to evaluate the things connected to it. So at this point, it's only connected to 3 other hydrogens. There's no other kind of interesting chemistries associated with that, so that's going to make that a zeroary or a methyl. Methyl's the default name. I like to call it zeroary. Halide. When we go through and look at the next one, same kind of deal, and what we want to go through and do is evaluate the components next to it. It may be important to go through and include those hydrogens so that we can extra see that and note that this one is now a primary. We move to the next one, again highlighting in purple that leaving group bond. We look at the connections, it's connected to 2 carbons, it's secondary. We move to the last one, we're looking at 3 carbons connected, so tertiary. Okay, and what I will do once we discuss these 4 is I'm going to go through and make a modification to a couple of these that we will then explore beyond our zeroary, primary, secondary, tertiary. So if we're concerned about carbocations, so let's start with that. If I want a carbocation, it needs to be stable. So my first argument to go through and do would be, hopefully I memorized the stability of carbocations. I want more electrons around them. So a carbocation is unstable because it is a positive charge. To make it more stable, it needs more electrons. When I compare from 0, primary, secondary, tertiary, the tertiary has more electrons around it because we're looking at carbons versus if we jump all the way down to the zeroary versus hydrogens. So what does that mean for us? If we're going to run a one-type mechanism, we would predict that one-type mechanism to occur in the tertiary sense and the secondary sense. Okay, when we talk about zeroary and primary, those are so unstable we don't expect the one-type mechanism. I'm going to make a quick edit to that steric hindrance statement. Hopefully that edit will make sense here in a little bit. So what we're trying to do is call attention to the different types. So our one type will be blue, and then we'll reference our red type as a bimolecular type mechanisms. So we've labeled out our one type mechanisms. And if we went through, we can go through and put a cross on those. Those aren't expected to form zeroary or primary as far as carbocations go. If we now look at the 2-type steric hindrance, I'm concerned about the backside attack, the backside of that leaving group bond, what is back there? Okay, so if we kind of draw in that red line, hopefully what we can go through and see is that number 1, there's always going to be bonds back there. So we aren't referencing the bonds, we're again referencing the atoms that are connected back there. And we go through and look, the difference between those is again carbon versus hydrogen. Carbon having more electrons, I'm going to want a backside with just hydrogens. So the 2-type mechanisms will work for our zeroary and our primary, and will ultimately fail for our tertiary, or at least have a very hard time of it. Where we're going to run into a slight issue, though, is the secondary. The secondary really works equally well or equally poorly for both the 1-type and the 2-type mechanisms. Okay, so we've now got kind of a bulk classification for our substrates based off of rates, okay, be it first or second order rates. And we are going to run into kind of a weird exception here, because what we've really just done is referenced for our substitutions. We haven't really addressed eliminations, and we'll see why that becomes a problem here in a second. If we're going to try and differentiate between substitution versus elimination, so now we've got our 1 types labeled up there and our 2 types labeled up there. What happens if we now add in the concept of our substitution versus our what color elimination? Okay, well, in the substitution, we're looking at a nucleophile. Helps if we use proper coloring. We're looking at a nucleophile. In the elimination, we're looking at a base. In the elimination, it's the formation of that pi bond that helps kind of distinguish. That pi bond is going to be our real differentiator between our substitution and our elimination. That pi bond is going to suggest that what we want to be looking for is stable pi bonds. Stable pi bonds form when they are more substituted, which means if we're going to look at substitution and elimination, I want a pi bond where there's more carbons. Eliminations are going to be more prone in the secondary and primary. Okay, there's the potential secondary and tertiary. There's the potential at the primary, but it becomes difficult, and the elimination is impossible off of the methyl because there's not a place to make a pi bond. Okay, if we look at the substitution, well, the substitution could really happen in any of these as far as overall reactions. So that adds a whole layer of kind of difficulty behind this, because if we stack all that information out, substitution happens in all. It's now just a question of which mechanism. This is why we started with the 1 versus the 2 type, or where I started there. Okay, so if we now go through to summarize under all of these, if we look at a zeroary, we really only get one option. We get the SN2 type mechanism. If we look at our primary, we get the SN2, and to a lesser extent, we can get the E2. It's possible, okay, but it's at the low end of its probabilities. If we move to the secondary, everything shows up. We get the SN, oh man, I was really trying to color code this, wasn't I? We'd get the SN2, we'd get the SN1, we'd get the E1, and we'd get the E2. So we get all of these possibilities coming out, which is why when you see a secondary substrate, it's going to kind of suck, because you get all 4 options coming to the table. Okay? And there's nothing to really nuance those based off of the substrate. If we go through and look at the tertiary does simplify out. We'd get the SN1, and we'll get the E1. And I'm going to go ahead and erase that slide number 67, and I'll write it in the upper right hand corner. Okay. And remember how I said it was a bit misleading when I crossed out that 2 type? The elimination has slightly different demands on it. The E2 does actually form quite effectively when it's tertiary, and that has to do with that substitution. We're forming that more stable pi bond. That difference between the pi bond versus the sigma bond formation is really what differentiates that. Okay, so if we now go through and look at it, we now have, based off of those classifications, the kinds of mechanisms that we would expect to happen in each of those. If you're wondering why we came to those certain conclusions, I did try to talk through some of those, but the details and nuances behind that are better found when you're looking, at the specific overview videos for each of those individual mechanisms. Okay. So with that, let's go ahead and throw some curves in on this. So I'm going to pause the video and draw. So what happens with these new structures? Okay, so let's consider first our 2 type. Well, we really aren't changing the backside of the bond in either of these cases. Okay, so really the effects of what I've drawn in aren't a huge issue to the 2 type mechanisms. Either the SN, well, it's going to affect the E2, and we'll address that in a second. But it doesn't really affect the 2 type mechanisms, be it SN or E2. So we're still running based off of the bulk classifications of these, with this one being primary and this one being secondary. They're still going to have the same end results with our SN mechanisms, or our 2 type mechanisms. The 1 type mechanisms are going to become the real question here, because with this added change to the structure, if I go through and put in a positive charge, because it's a carbocation, okay, and I think the 1 type I said was blue. So if we have the leaving group leave and we now form that carbocation intermediate, is there something else that can contribute to the stability of the carbocation beyond just the substitution? And of course, our favorite 9-letter word, yes. Both of these structures exhibit resonance contributors. Those resonance contributors are going to change the overall stability of the carbocation significantly. So now the question is going to become, or at least the question I'm going to ask, would be how significant of a difference is it? Well, should it be more significant than the substitution patterns? So that would be the easiest place to start. Okay? In a substitution pattern, all we're talking about is what are the atoms next to it that can sort of share electrons in. Now, they aren't formally sharing, and therein lies our answer. When we look at resonance, resonance is a formal sharing of electrons. Electrons are actually moving. When we look at the substitution patterns of primary, secondary, tertiary, there's not a formal sharing of electrons. It's just that there's electrons nearby. Resonance is going to be a much larger contributor to the overall stability of a molecule than will substitution. Okay, how much of a difference? Well, if we look at our tertiary being more stable than secondary, more stable than primary as far as carbocations go, okay, where would we throw in resonance? And in fact, we'll just throw it in here. Primary with resonance, depending on the experimental setup, can be more stable or similar in stability to a tertiary structure with no resonance. Secondary with resonance will be better than primary, and tertiary with resonance will be the best of all. Okay, so those resonance contributors make a huge effect to the overall stability. Okay, so much so that we tend to reference them as a different name. That different name for our resonance contributions is really going to come into play with that secondary structure. And what that gets referenced as, that carbocation, is located at an allylic position. So allylic is 1 carbon removed from a pi bond. Okay, and I wish I had a statement of alpha, beta to kind of help with that, but I don't think I do. Okay, the allylic position would be 1 sigma bond. There's 1 sigma bond removed from a pi bond. Okay, so that red atom is allylic. If I add another carbon on it, call it that green carbon, that green carbon is now 2 sigma bonds removed from the pi bond, and it has no interesting chemistries because we won't be able to get resonance out to it. Okay, so allylic is the name that you might see for that. If we go through and take a look at the other structure that we've got our purple bond, and then there's our parent pi bond. We're still in that one sigma bond away for that carbocation. So it could theoretically be called allylic. But that pi bond is part of a larger system, a larger pi system. Okay? And that pi system has such interesting and neat chemistry that we specifically reference that aromatic chemistry in second semester. Because that chemistry is so distinct from just a standard pi bond, this gets a new name, and that position becomes known as benzylic. So same concept, it's one sigma bond removed from the pi bond to the carbon that you're referencing, okay? But now it's called benzylic because it's the benzene ring as opposed to allylic because it's the alkene, okay? So that makes a big effect in our carbocations, and it's one that tends to trip up students because you tend to just memorize this tertiary, secondary, primary, which is the smallest effect. So what we could do is throw on a structure like this with our chlorine and be like, whoops, helps if we did that right, and say, would we expect an SN1 mechanism? And we'll get a lot of students saying, no, there's no SN1 because that's primary. Draw out your structure. We have a resonance contributor. It's not just primary, it's primary with resonance. So yes, it should happen with an SN1 mechanism because of that carbocation stability. Okay, and that's where that's coming from. So I think that was actually new. If we go through and look at this slide is a repeat of the old one, so we could go through and look at this one, but it's ultimately not going to be a huge issue. I do want to address the middle structure because the top structure should be our allylic. So hopefully you see that pi bond. Whoops. We've got our pi bond and then our sigma bond. So this carbon is allylic. If the leaving group leaves with electrons, we would then have an allylic carbocation. Okay, so that makes it stable. If we go through and look at the bottom structure, we've got our pi bond, our one sigma bond away. That position is now benzylic, and so should be reactive. And so both of those will react under SN1 and SN2 conditions. SN2 largely because they're primary substituents. But what about the middle structure? So if I go through and look at this, doesn't this still have characteristics that we just addressed? Okay, because if I go through and evaluate that, isn't that now saying that that position is in that pseudo-allylic representation? Okay, and the big issue there is no, we also have that pi bond contributing. Okay, and this is where this one gets tricky. If we try to draw this out and say the leaving group left, we end up with a positive charge at this carbon, and students will ask, well, can I do resonance? No, because to do resonance you have to have overlapping p orbitals. There aren't overlapping p orbitals because the p orbitals of that benzene structure, if we kind of take this and rotate it up out at us, there's the p orbitals of the pi system. When we remove electrons, that bromine from the side, what happens is that that carbocation is now attempting to form in a perpendicular orbital. It's now in the plane of the paper. Okay, so it is perpendicular to the ring pi system and thereby cannot be stabilized by the ring pi system. We might then try an argument, well then couldn't it be stabilized because it's a secondary carbon? Well, that also falls apart on us for a couple other reasons. The hybridization of that carbon now becomes sp once our leaving group theoretically leaves. The sp has a very high electronegativity, so much so that it is not going to be positive. Okay, why does the electronegativity go up? Because the S character goes up as well. Okay, so it can't stabilize a positive, much like an oxygen. Okay, so that means that structure can't form. Well, if that structure can't form, the bromine can't leave. Okay, so we get a new name for that position, which I had in my head and then I just lost. I don't actually remember what it is, but what we can go through and do is we can refer to that position by the hybridization. An sp2 carbon with a leaving group won't react. So leaving groups connected to sp2 are non-active. We'll sort of see an exception to that a little bit later, but if you treat them as non-active, you should be good for the bulk of the semester. We've got our summary down below showing our tertiary, secondary, primary allylic, and then this is really supposed to be summarizing for our one type or unimolecular type reactions, because you'll notice you don't see the primary and zeroary on there. This is in reference to just carbocations. Okay. After that, we've got our leaving group ability. We'd say why pick bromine as a leaving group, and we picked it in the case where we had just connected to hydrogens, and it's going to run into the same situation that we talked about in that video earlier. The bromine, if it acts as a leaving group, is going to produce Br minus. If one of the hydrogens acted as a leaving group, they'd be producing H minus. So remember, the leaving group leaves with electrons, so it needs to come off as a negative. H minus is incredibly unstable. Why? Well, the first thing we could do would be look at charge. And you say, well, bromide's also charged, so let's push that further. The next thing we would look at is size. Hydrogen is literally the smallest atom. If we looked at that single electron on bromide and its reactivity, there it is. If we looked at hydrogen, there's that single electron in it. Which of those circles are you going to stick your hand in? Okay, you're probably going to avoid the hydrogen one because you're very likely to impact that electron. That makes that electron exceptionally reactive, so much so that the chemistry of the hydride H minus becomes its own story, and we'll address that when we need to, either this semester or next. Okay, so when we're looking for our leaving groups, we're looking for groups that are able to leave, okay, or take electrons. So the easiest thing to do would be to look at high electron or electronegative elements, because they're going to withdraw electrons. It's a good thing to focus there also, because that generates a polarity, and that polarity tends to be where our chemistry is going to occur, because we want to neutralize that charge. Other characteristics, they need to be weak bases once they've left. They should be polarizable and big. Really, these kind of rules that we're addressing here are all already addressed in the rules that I've told you to memorize as far as reactivity. Evaluate charge, size, electronegativity, resonance, induction, and then hope you don't have to deal with it. And let's just say hope. Okay? If you go through and use those things to evaluate the stability of that leaving group, that will help you, particularly in cases for that one that I've got drawn up here. Which of those things is the most likely leaving group? Bromide, because it's the largest. Okay, there are going to be definitive lines that you have to worry about. Okay, for instance, hydroxide, not a good leaving group. Okay, why is it not a good leaving group? Effectively, we're memorizing it. One of the things that could help us with that is it needs to be a weak base. Hydroxide is by definition a strong base. Okay, so when I want a leaving group, there is going to be a line of, that's not good anymore. That's going to come with practice and seeing a bunch of different structures. A lot of what you'll see, at least in this unit exam and for the rest of this semester, is not testing you on that hard, fast line, but asking you to make that comparison between these two leaving groups, which one's the best. Okay, so that should help a little bit. To that end, we could go through and look at a structure like this and say, I want to run the elimination reaction where I make the pi bond. And so one of the kind of default responses is to go, well, that's an elimination. I remove the hydrogen, I kick off the leaving group, and I get hydroxide. You might say, well, hydroxide's a bad leaving group. Again, how do we know that? We really only know that with experience. So how would you be able to predict what to do with this or to help this reaction along? Okay? To decide, look to that other reagent. Almost always this reaction includes H+. Okay? Why would it include H+? Well, hydroxide is such a bad leaving group that the very first thing we do is not perform the elimination, but we instead perform the acid-base reaction to turn the hydroxide into water. Now it is a great leaving group, and now I can do the elimination. So recognizing what your other reagents are doing, why they are there, will help key you off to when you have a good leaving group versus when you don't. If you see nothing there, then it could very likely be that you're just allowed to do your normal leaving group chemistry. If there's something else written there, you should at least consider using that as a reactive species to make something better in the course of a mechanism. Okay. Solvents. Solvents are always a tricky one to deal with, and really the big thing that you need to be able to recognize here is being able to classify. We've got 3 categories, okay, which I really probably should have just written out, but we have 3 categories: polar protic, polar aprotic, and non-polar. Since your protics are almost always by definition polar, or they are by definition polar, you can get away with these 3 categories: protic, polar aprotic, and non-polar. Okay? Where are those coming from? Those are coming from the intermolecular forces generated from the bonds, which is all back in Unit 1. The roles of our solvents, they're typically a hidden role. They aren't explicitly shown in our mechanisms, and we're really just kind of expected to have recognized why it was important. How do we know that? Someone tested it in an experiment, which then means we have to memorize it. Okay? I will say I tend to be less particular on solvents, so that if I want you to ask or answer a question about solvents, I'm going to explicitly ask it about solvents. If I'm asking a question about something else, the solvent probably won't play a role. So there's 2 primary reasons for solvents. We want to get all of our reagents into the same phase, so we want a homogeneous system. And then secondary roles are largely, they're there to stabilize reagents or intermediates so the reaction can happen. But in some cases, it's a destabilization that allows us to say that that was a bad solvent, or maybe even a good solvent. Okay, so if we go through, you should be able to classify your solvents. Okay, so looking for those characteristics: protic, aprotic, nonpolar. Because that was in the video, I'm not going to discuss it. So when we're talking about our individual mechanisms between either SN1 or SN2, which is our primary characteristic for it, is we want to be thinking about the characteristics of our SN1 and our SN2. So for instance, in the SN1, our primary focus is the stability of a carbocation. Whereas in the SN2, my primary focus is in the stability of the nucleophile. Okay? Where is this important? Well, the nucleophile was a reactant, and the carbocation is an intermediate. And this becomes important as far as our reactions go, because both of those are charged species, so they would fit in kind of that salt compound. So if I'm looking for the best type to dissolve a salt, I want something that is as polar as humanly possible. Okay? And that's where I might push to things like acetic acid or methanol, because those have that protic aspect behind them. Okay? The problem with those, or just saying, well, I just want it to dissolve everything, is I also have to recognize where those reagents are falling in our reaction. A nucleophile is a reactant, meaning if I throw in a protic solvent, I will stabilize and dissolve that nucleophile. The key word be stabilize. If I stabilize it, I'm going to slow the reaction down. So that's not a good solvent for the SN2. For the SN1, we're forming a carbocation, and we might go, well, again, I don't want to stabilize the carbocation. The slow step of the SN1 is the formation of the carbocation. So if anything, I do want to stabilize it, because then that formation happens faster. So it's all about looking at our energy diagram and deciding where we are. For the SN2, we're starting here. For the SN1, we're starting here. If I stabilize the reactant, my activation barrier goes up. That slows the reaction. If I stabilize the intermediate, I decrease the activation barrier and the speed of my reaction goes up. So depending on where we're looking at those individual species, we're going to kind of expect the solvent to be doing different things. Okay, so this is where the carbocation really comes in. We want a polar solvent for the carbocation because it generates the largest dipoles, which means we're going to get the largest negative to stabilize that positive. Okay, this is where we have the solvents placed in this case is largely for our nucleophiles. Nucleophiles need to donate electrons. Solvents can stabilize those charge in electrons. So depending on which solvent we're using, that can F with our nucleophiles. So if we take a look at the example shown here, hopefully you can detect or guess that what we're looking at the top one is water as a solvent, which is a protic solvent. And the bottom one, little bit trickier to detail out, but hopefully you can tell that that is acetone. And if you don't know the common name, that's okay. CH3, carbonyl, CH3. I don't know why I had to draw that bond there, but I did. And this would be polar aprotic. And so what we're trying to address in here is how is that solvent affecting our nucleophile? So in this case, that negatively charged species. If we're looking at a protic solvent, what ends up happening? Okay, that protic solvent is going to align where those very large partial positives are going to interact with the negatives. Okay, so if we compare, you'll notice that we have the same number of these in each case. Okay, so we have that interaction. But is that interaction the same strength? Well, chloride is more electronegative than bromide, which means the negative charge on chloride is more compacted, okay, or stronger, which then means the hydrogen positives are more strongly attracted to it. Okay, so for the chloride to act as a nucleophile and react somewhere else, we have to break those very strong interactions. So the solvent actually hinders the nucleophilicity. Let's just say that says philicity. Okay? So in protic solvents, we actually want less electronegative atoms or less electronegative nucleophiles. Those end up becoming the more nucleophilic. If we switch it up and look at polar aprotic solvents, well, now in that aprotic environment, you've weakened that interaction so much that now what is dictated by our interactions is the amount, the sheer number of particles of solvent molecules, which should be in green in this case, of those solvent molecules around an individual nucleophile. And because bromide is significantly larger, there are more nucleophiles in the way. With more nucleophiles, or sorry, not nucleophiles, more solvent in the way of the nucleophile. So if there's more solvent in the way, well then that means that nucleophile gets hindered. So what does that mean? Well, when we move to aprotic solvents then, the larger the nucleophile, the less nucleophilic it becomes. Okay, so in a polar aprotic, chloride is your stronger nucleophile. In a polar protic, bromide is your stronger nucleophile. So note it changes. Okay, What makes this even more frustrating, I think, to deal with is that this effect changes for virtually every class of substance. And we're making similar comparisons, but it becomes very tricky to nuance exactly where that line is. So my argument is, when it comes to nucleophile strength, avoid worrying about solvents, just play it based off of how we've discussed nucleophiles. Okay? Well, how have we discussed nucleophiles? That's this next slide. Look for your nucleophile strength in those red boxes. Those are the big tip-offs that you need to be memorizing. The harder ranking in 4 is dealing with that solvent dependence, and that becomes very, very, very tricky to nuance. You're probably looking at most 1 or 2 questions. Okay? So don't stress a whole lot there. If we go through and look at the rules, ideally what these rules should be mimicking would be charge, size, electronegativity, resonance. And sure enough, they do. It's just in a slightly different format because I haven't committed to fully shifting to this charge, size, electronegativity, resonance. But if we go through and look at it, the very first rule, negatively charged. Nucleophilicity decreases from left to right. You'll notice we're skipping size to look at electronegativity. Why? Because the size really becomes an issue with our solvent. Okay? So our size can mess with our understandings there. The resonance, if there's more resonance, that weakens the nucleophilic character, and so it's not as good of a nucleophile. Same deal with induction. It's pulling the electrons into the structure. The last one becomes a challenge, and that's steric hindrance. Why that becomes a challenge is you're trying to nuance the difference between nucleophiles and bases. Okay? That big difference is that nucleophiles donate to things other than hydrogen. Bases donate specifically to hydrogen. Why does that matter? Well, hydrogens are found on the outside of the structure. Electrophiles, things other than hydrogen, are found on the inside of the structure. So if I have a negatively charged species that is small, that negatively charged species could theoretically get in to attack that electrophile. It could just as easily just react with the hydrogens on the outside. So that small species has both pathways, and trying to figure out what I'm trying to write, has both pathways available to it, and that's why it becomes challenging. But what happens if we scale up to something like this? Well, now this is a classic large solvent, has this giant group here. As this tries to come in to get to, say, that electrophile, it gets butted up against these other carbon structures, which means it ends up effectively only going towards our hydrogens. Okay? It can only get to the hydrogens, which means that species can only act as a base. Okay? Yes, we can always force these things to do other things. Okay? But the primary focus there is that that's going to be a pretty exclusively a base. This is typically written as T-butoxide. Okay, why T-butoxide? What's a common name? The carbon in the middle is a tertiary carbon. There's 1, 2, 3, 4 carbons. There's the bute. So T-butoxide, if you see that T-butyl, that's a pretty big sign that you're looking for a base, or you're looking at a base, not a nucleophile. There are other bulky bases. This thing I think is DBU, DBN. I'm not positive. Okay. Those abbreviations I don't expect you to memorize. If they pop up, I will give you those structures. I do expect you to be able to evaluate why they're basic. Why might this one be basic? Everybody's favorite. When you draw out a resonance structure, what happens to that terminal nitrogen? It becomes negatively charged. That is now a strong negative charge, which can act as a base. And I'm not going to draw a 7-membered ring freehand. Okay, that atom is now my strong base, and it is massive structurally, which then makes it a strong base. Okay, and just for giggles, I'll throw it on here and leave you to think about it. Sodium hydride is also one of the most sterically hindered bases there are. Okay, so that's one you'll probably see in second, or discussed in second semester, but you're welcome to kind of press me on that in the digital office hours or in the notes. Common nucleophiles, your textbook has kind of summaries between these. You're just looking for those negatively charged things. The one thing that's fun is your halides will only act as nucleophiles. This is why most books or most textbooks organize based off a functional group, and we'll talk about alkyl halides early on, because we can do the halide chemistry with substitution reactions and not have to worry about eliminations, because the halides can't act as bases. They can only act as nucleophiles. So it simplifies things. With that, we've covered all of our kind of basic pieces again, and the rest of our slides are either review slides, or we're going to get into some kind of interesting topics, and I'll save that as a hodgepodge of interesting things in another video.